Hello and welcome to this short video to finish off lecture 8.1 or topic 8.1. We're going to look at a few questions relating to the material from the first lecture, the fluids lecture, which covered pressure mostly. So we'll jump over to the lecture slides and we'll have a look at the first question and discuss how we might solve this. The question is about a water storage tank. So a rural house that's not on town supply has a tank of water that's been raised up. Right, it's raised so that we have this pressure pushing downwards so that it comes out of the tap when you turn the tap on. And the question is, what is the difference in water pressure between the tap and the surface of the water in the tank? So this comes back to the idea that as long as a body of water is continuous, is connected right through, then the pressure is determined only by the height or depth below the surface of the water. If we wanted to know the actual pressure at the tap, we would need to know whether the top of the water is exposed to the atmospheric pressure or a vacuum or what it's exposed to. But we're not asked that, we're just asked about the difference in pressure between the tap and the surface of the water. And because we can assume it is a continuous body of water, we can assume that because if it wasn't, we would have no way of solving this problem. So assuming it is a continuous body of water, all that matters is the height, and they've given that to us. So there's actually not a huge amount for us to do on this. It's essentially going to be a math problem. So we've got rho for water. It's a water tank. So we have 1,000 kilograms per cubic meter. We've been told H is equal to 30 meters. We haven't been told how many significant figures, but I would assume 2 because 1 is not very useful for us as in order to do a calculation. And we've got gravity is equal to 9.8 meters per second per second. So then we just have pressure is equal to rho g h, and we multiply those together. So if we multiply them together, then you can get the calculation. So if you have got a calculator, do that now and see if you get the same result. But obviously doing a calculation is pretty simple at this point once you've got everything sorted. And you should hopefully get out that it is 29,400 Pascal, which we would write as 29 kilopascal, right, 2SF, because as I said, 30 is most likely given to 2 significant figures anyway. Or you could write that in scientific notation, 2.9 times 10 to the 4, wouldn't it be? 10 to the 4 Pascal, if I've done that correctly. But you can write that however you want. And if you remember that 1 bar is 1 times 10 to the 5, that would be 0.29 bar. Right, so there's several different ways you can write that. But the pressure coming out the end is what actually matters. So we'll go back and we'll have a look at the next question. Right, so that was a fairly straightforward one, just making sure you're happy with that calculation and the concept of just needing the height in order to get that pressure. The next question is about a barometer. We saw that for a mercury barometer, you only needed 76 centimeters in order to match atmospheric pressure. Right? So remember, the barometer used the pressure at the bottom of the column, which was just due to that column, and matched it with atmospheric pressure so that they were equal at the same height or same depth. In this case, in this question, they're asking us how tall would the column of water need to be to make a barometer out of water that was otherwise designed in the same way. So this one we'll start with a bit of a diagram. We'll think about what's going on here. So remember, the barometer was essentially something that looked like this. Right, and we had some liquid in the reservoir, so this was our reservoir of liquid, but the liquid also went all the way up here, right? And we said that in this space in here we have 0 Pascal with a vacuum, no pressure at all, and pressing down on here we have 1 atmosphere, right, which is 101 kilopascal. So that's our pressure on that surface. Right. And of course we know that the pressure anywhere along that line, so anywhere along here, is going to be the same as it is here. Right, so the pressure anywhere along that line is going to be the same. And so then we just have to think about how we equate these. Right? The pressure at this point So I'm going to call this point A. The pressure at A is equal to, because we've got no pressure at the top, it's just equal to the height of the column of liquid. So it's just equal to rho GH, right? Plus our 0. I'll just write that in to be really explicit that we've got 0 pressure pushing down on the top. And then if we call this point here B, pressure at B is equal to 1 atmosphere. Right? That means that because A and B are equal, we can say that those are equal. So we have that 1 atmosphere is equal to rho GH. Now, we wouldn't actually know how tall H needs to be unless we know the actual atmospheric pressure, but we know that it's usually around about 101 kilopascal. So the question is, how tall does H need to get in order to measure or to match that 1 atmosphere? So if we have 101,000 equals, for water, remember we've got density of 1,000 times 9.8 times H, and then we can just rearrange for H. So H is going to be equal to 101,000 over 1,000 times 9.8. And again, if you've got your calculators, at this point, it's just a matter of doing a calculation. But hopefully what you get out is 10.3 meters. So that means that in order to make a barometer like this, where the top is at a vacuum and the column of water is purely responsible for matching atmospheric pressure, for making this the same here and here, this column here needs to be 10 meters tall, well, over 10 meters. Now, it doesn't have to be very wide, so you could set one up. You could build one. We could put one down the side of the science towers, but it's very difficult to read. It's difficult to maintain. It's not very practical. So that's why we often go with mercury, because mercury having a bigger density, since we still have same atmospheric pressure, same gravity, the bigger density means we can have a smaller height. And mercury obviously is a nice dense fluid. It is more dangerous, so we have to take extra precautions, but it means that we can have a nice portable barometer that we can actually move around and set up without too much hassle. So there is one more question. So that's our water barometer. The last question is about a suction cup. We've got a 10 centimeter suction cup, or 10 centimeter diameter suction cup, against a perfectly smooth ceiling, and all air is expelled from within the cup. The question is, how much mass can the suction cup support before it will detach from the ceiling? So this one might be a little confusing to start with, but let's just stop and think a moment about what a suction cup actually is, how it works. So the idea is that you've got a ceiling, right? And I'm going to draw a couple of different ones. So this is different points in time. So we've got our suction cup here, and it looks something like this, right, with our rope hanging off the end. And at the moment, this is full of air, right? Remember, little air particles are just flying around everywhere, right? So this is full of air. It's got air pressure in here, and out here is still air pressure too. So here we've got air everywhere, and that means that the air inside and outside is both colliding with the suction cup. And so there's force inwards and outwards on the suction cup. But the idea is that if you take all of this air, all of these air particles in the suction cup, and get rid of them, send them out of the suction cup, what happens is that the suction cup will end up being all flat because it's now got no air in it. Right? So now in here, we've got pressure equal to 0. And then we've still got our string hanging on it. Right? The question is, how much can we pull down on this before this will detach from the ceiling? And then to understand the answer, you need to think about what's actually keeping the suction cup there. So we've still got this pressure from the atmosphere pushing on the outside of the suction cup, pushing upwards on it. And now pushing down on it is nothing because there's no air left inside it. So that means we've got a one-way force. We've got force only going upwards due to the air. So the reason a suction cup stays there on whatever surface you attach it to is because of the atmospheric pressure pushing on the outside being greater than the pressure on the inside. So now with that concept hopefully making sense, we can actually calculate that difference in pressure. And from the difference in pressure, we can calculate the difference in force. So what is the difference in pressure? Well, hopefully you already know it, right? We've said that there's 0 pressure inside, and outside there's 1 atmosphere of pressure. or 101 kilopascal. So if we've got 101 kilopascal pushing upwards and no pressure pushing downwards, then that means that we can figure out the force, because they're both applied to the same area. They're both applied to a 10 centimeter diameter circle. Right? So the area, this is looking top down now, the area of this is going to be pi r squared, right, or a quarter pi d squared if you prefer. Either way, you can calculate the area of our suction cup. Then before we, if you want to, you can calculate it. As I've said, I often prefer to work algebraically through it and then do one calculation. So we know our area now. We know the area is this. We know the pressure difference is this, right? And so now what we've got is that our pressure is equal to a force over an area. So the I'm going to call it pressure inside and pressure outside. So pressure inside is equal to 0, and that means that the force inside is equal to 0 times the area, which is going to be obviously 0. So there is 0 newtons pushing down on the suction cup. The pressure outside is 101 kilopascal, which means the force is going to be 101 times 10 to the 3 times a quarter pi d squared. So now we can actually calculate that force pressing up on the suction cup, and that is going to come out to, if you've got your calculator and following along, hopefully you get the same result as me, 793 newtons. So that means that on our diagram, we have an upwards force. So actually it's a bit hard to draw onto that diagram. I'll draw a new one. We've got our thingy here. We've got a force upwards of 793 newtons. We've got no downwards force yet, because we said that it's a perfect vacuum inside, and we're also ignoring the mass of the suction cup at this point. But there is a string, and we can hang a mass from that string, and that's what the question is asking us. How much can this mass be? Well, in order for this suction cup to stay there, the tension on this string can't be any more than that force upwards from the environment, from the atmosphere. So that means that the tension has to be less than or equal to 793 newtons. And of course, we know the tension in the string, again, assuming idealized strings, so our usual physics assumption that this is a massless, inextensible string and all of that, we have the mass times gravity is less than or equal to 793 newtons. So the mass is less than or equal to, we divide 793 by gravity, right? So 793 over 9.8. And that will give us whatever that comes out to be. I can't remember. I'll just check. Hold on. If you've got a calculator, do it. I will check because I've already calculated it. And it comes out to be 80.9 kilograms. So about 81 kilograms would be the maximum. Remember, of course, that is an ideal suction cup. Right? We cannot actually get to 0 in here. Right? Getting to 0 inside the suction cup is practically impossible. And it also has ignored the mass of the suction cup itself, the impurities in the sealing. If the seal isn't perfect, then you will get some air being able to get in and out of there, and that will obviously release the suction cup. If you've got the string itself not being perfect, then that can affect it. So there's all these different factors. This equation is an ideal one. So in reality, a 10 centimeter suction cup would never get up to 80 kilograms, but it gives you an indication of the sorts of masses that we can hang on these sorts of things. So that's the end of the questions for this lecture. Just fairly basic ones, but hopefully reinforcing those concepts that we've talked about, and hopefully putting you at a point where we can now move on to the next topics and take this stuff as our base knowledge that we all agree with and just accept.